Okay. Good morning. I'm Kiran Kumar V, Vocational Association Professor in the Department of ISC. So I'll be handling the subject data. So in that, we'll move to our second module. In second module, we have a general method. We need to study about the recurrence relation. Next, algorithm binary search. So we'll be applying. We will see how the binary search algorithm works. Okay, and also we'll try to analyze it. What is the time taken by that particular binary search algorithm using divide and conquer technique. But first, we'll study what do you mean by divide and conquer technique. In divide and conquer technique, what we are going to do, there will be a problem of size n. You're going to divide this into n by 2. You're going to divide it into n by 2. And further, what you're going to do, you're going to divide into 1 by 2 until and unless you're going to get only one element. Then you're going to find out the solution to the subproblem. That is for the left hand side of the subproblem. You're going to find out the solution for the right hand side of the subproblem, and then you're going to combine and you're going to find out the solution to the original problem. So this is nothing but what you call it as a divide and conquer technique, where you're going to divide, you're going to conquer, you're going to combine. So it is DCC. Okay. Now this is the algorithm, a general algorithm for divide and conquer, where they are going to ask this for 6 to 7 marks, where it's an algorithm divide and conquer. You're going to give a problem. If the problem is small, then you're going to return. Okay. Else you're going to divide that into instances. Next you're going to apply divide and conquer recursively to the subproblems, and later, after finding out the solution, that is what we studied here. After finding out the solution, you're going to combine that to a solution. Okay, where DAC of problem 1, DAC of problem 2 till problem k, you're going to combine that to a particular, and you'll get a solution. Okay, now here in the mathematical analysis of recursive algorithm, there or mathematical analysis of non-recursive algorithm, there we were trying to find out the summation. Next we were trying to get the values, okay, in terms of a recurrence equation. We are trying to get a recurrence relation in mathematical analysis of recursive algorithm. Now here again same here in terms of divide and conquer. Now from the previous two slides you understood what you mean by divide and conquer. Now how to get a recurrence relation for that. Okay. Now if the problem is for size p, then the sizes of k subproblem, that is you're going to divide it into n of k, then t of n equals g of n, that is a function, that is it gives some value if n is small, else okay, t of n1 plus t of n2 plus nk plus f of n otherwise. So t of n is the time taken for divide and conquer method. G of n is the time to compute answer directly for the small inputs, so that we have seen. Next, a function f of n is the time for dividing a problem and combining the solution. That is what happens in divide and conquer, right? If the problem is small, what happens? Directly you're going to write, say 1 or 2 or 3. It will be some constant. Whereas in terms of t of n, in terms of divide and conquer, you're going to take any input of size n. Next, a function f of n where you're going to combine. Okay. Next, generally an instance of n will be divided into b. So the value will be n by b. So assuming n equals b per k. Okay. So here you're going to get t of 1 where n is 1. At n by b plus f of n if n is 2. F of n is a function that accounts for time spent for dividing the problem into smaller ones and combining the solution. So this is with respect to the some searching techniques or applying the divide and conquer. Okay. Now this is considered the case in which a value is 2. That is a value is 2. That is here what we say at n by b plus f of n. So what is the value of a? The value of a is 2. B is 2. Okay. Now how to go about that? If t of 1 is 2, f of n is n. Okay. Then how to go about that? Next, similarly, this is a recurrence relation. How to solve this? That is, you can also solve using substitution method, and also you can solve using the Master's theorem. Okay, now this is the master's theorem. If A equals B power D, okay, that is what we did here. Okay, that is 2t n by b. Now if A equals B, okay, A equals B, okay, then it is theta of n power d log bn. Okay, n power d log bn. Now here, as you can see here, it is 1. Okay, it is n power d. Now n power d can be taken here, d can be taken as 1. Okay, so n power 1 log b log 2 to base n. So n log n is for 2t n by 2. Similarly, for this t of n by 2, a value is 1, b value is 2, plus there is some constant. Okay, now for that, if a is less than b, you are going to get n power d. So you are going to get approximately n. Okay, you are going to get n. Got it. But what if the value of a is greater than b power d? Okay, its value is, then you are going to get log ba, that is n power log 2 power base 2, that is n power 1, that is n. Okay, here I am telling about 2t n by 2 where a equals b power d. Now what is d? D value. The d value here in this case is 1. Okay, but here if it is 2a plus 1 plus 1. Okay, now let's move to a binary search. Now what do you mean by a binary search? The binary search here, the problem definition. Okay, so here let's consider ai where I value will be somewhere between 1 to n with a list of elements that are sorted in a non-decreasing order. The problem is to find whether a given element is present in the list or not. That is the key element. If x is present, we have to determine the value of j, that is where exactly the value is present. If it's not in the list, then you're going to set that to 0. Okay, this is a binary search. Now how to go about that? In terms of a binary search, you have a problem p equals n, that is number of elements, followed by the elements. Okay, x is the key elements to be searched. Okay, this is the pseudocode. So pick an index q, okay, in the middle range. That is what you're going to do. You're going to mark low, you're going to mark high, you're going to divide that by 2, and you're going to get the middle element. Now what you're going to do, you're going to compare. What you're going to do, you're going to compare the element with respect to the middle element. Okay, if both are equal, if the x is equal to a of q, middle element, then the problem is solved. Else if it is less, again you need to perform the divide and conquer to the left hand side. If it is greater, then you have to perform the divide and conquer onto the right hand side. Got it? Okay, so next this is a recursive binary search. In binary search, here you have an array I is type x. Okay, that is a minimum element, and low and high. Okay, given an order a of I is to 1 in a non-decreasing order, determine whether x is present. Okay, so if low, if L equals I, then if x equals a of I, that is if it's a small problem where only one element or two elements are present at that particular moment, if small p, then you are going to return I if the key element is found, else you are going to return 0. Else what you are going to do, you are going to find out the mid position. If it's equal to mid, you are going to return mid. Okay, next this is with respect to the iterative binary search where low is less than high, int mid equals low plus high by 2. So here you are not calling. Okay, here just you are comparing, you are just placing the low element and the high element. Here you are not calling the function, so it is a iterative binary search. Now let us see the 14 entries, minus 15, minus 6 till 151. Now what is low? Now the x value what you have to find is 151. But where is 151? 151 is somewhere over here. Okay, now what is low? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14. Now what is low? It starts from 1 to 14. Okay, 1 high, then what is mid? 7. Similarly, okay, similarly here you're going to compare the element. Okay, since you're going to compare the element, where you're going to find that 151, it is greater than the mid. So again you're going to go from 8 to 14. Again you're going to move towards the left hand side, and then you're going to find out the mid, and again on the right hand side, again you're going to find out the mid, again you're going to go on the right hand side, again you're going to find out the mid. Now you'll find that the key element is equal. Okay, similarly here x equals minus 14. So what you're going to do, low is 1, high is 14. Okay, then what is the mid element? The mid element is 7. Similarly, low is 1. Again, the where is the element? Since it is the mid is 7, so we are going to compare. So it will be on the left hand side. Then we go on moving until and unless we get a value minus 15 such that the value of x equals minus 14 is not found. So you are going to return 0. Okay, now analysis. Now what is the recurrence relation? Now the recurrence relation is T of n equals T of n by 2 plus C. That is, you're not going to include both the sides. You're going to include only one of the sides. That is, either you're going to move towards the left hand side, or you're going to move towards the left hand side or right hand side. Next, analysis. What is the space complexity? Okay, it's an iterative binary search. There will be a constant memory space because you're not going recursively, you're not going to call the algorithm. Whereas in terms of proportional, it is proportional to recursion stack. Okay, now what are the advantages? Efficient on a very big list, can be implemented iteratively or recursively. Now what is the disadvantages? Interacts poorly with the memory hierarchy, requires sorted list as an input. Okay, because if you're going to get an unsorted list, first you have to sort using some sorting algorithm. Okay, you have to sort using the sorting algorithm, and then you have to do it. Okay, then you have to apply the binary search. Next, due to random access of element list, needs array instead of a linked list. Okay, so this is about a binary search. So we'll meet in the next class.